we've been doing effectively functional programming for a while through the whole lecture, although making lots of references to the fact that all these things that we're playing with are actually objects. I think this is the right one. So what is an object? In Python, an object is a value with 0 or more attributes or methods. So a floating point number is actually an object. X equals 10.0. And it has some things associated with it. The real value associated with it. There is no imaginary value associated with it because it's a float. But obviously complex numbers have an imaginary value associated with them in general. Here's a method. So these are called attributes. So these are, think of these as essentially data that's associated with an object. And here's a method. So this is something, give me what x is as an integer ratio. So this just means it's 10 divided by 1. 1 divided by 3 as an integer ratio, as you all know, are these two numbers. So this is the best way that Python knows how to represent 1/3 with 16-digit floating point precision. So 1/3 is that. Okay. A list is an object, and we learned about some methods on lists yesterday. We can append the number 4. We can see what that is. We can pop it off, et cetera, et cetera. So these are methods that are associated with the object that is of a list. And all of these different things, pop can have a very different meaning on one type of object than it has on a different type of object. Every object is an instance of what's called a class. And everything in Python is essentially an object. So it stands to reason that we should be thinking about object-oriented programming. And many times when you're scanning code that other people have written, they've created these classes and then objects around those classes that are going to be of interest and potential utility to you. So what are some advantages of object-oriented programming? First of all, how many of you are very comfortable and have used object-oriented programming a lot? How many of you have heard of object-oriented programming, maybe dabbled in it? Okay, and how many of you, this is the first time you've ever heard of object-oriented programming effectively? Okay, so that's pretty good. You'll have to, for those that know object-oriented programming, like the back of your hand, there'll be some stuff that I'm going to introduce here that you've heard before, but I'll try to keep it as Pythonic as I can. For those that haven't seen object-oriented programming, there may be a few concepts that are a little bit beyond, but I'll try to sort of aim towards the middle here. And obviously, if there are questions, stop me and we'll go into it. So think of objects as sort of encapsulating the implementation details around something that you're going to wind up doing a lot. And it allows you to organize code very intuitively and keep data that's associated with a certain object very close to that object. And it's also kind of gives you modularity and forces you to think about modularity in a way that functional programming doesn't necessarily do for you. So we're going to use the paradigm of a bear for introducing object-oriented programming and the Pythonic way of doing that. So what is a bear? It's an object, right? It's an animal. It has characteristics, so these would be called attributes. Some of them have names. Some of them have color of their fur, the height, their weight. Bears do things like they eat and they sleep, and they cheer if they're at cow. And they have interactions with other bears and potentially other animals. And so all of these things you think of as attributes and methods that are associated with that thing. So we're going to create a simple bear class here, and we're going to do things. The blueprint for the bear class will wind up being, let's say, the attributes being name, color, height, and weight, and methods will be eat, sleep, and growl. And then we say, when we have a class and we create versions of that class that are specific, those are called instances. So we're going to create an instance of a Yogi Bear and a Winnie Bear. And so the attributes might be name, brown, 1.8 meters, and 80 kilograms. It's going to have methods associated with it of eating, sleeping, and growling, et cetera. Okay? Any questions about sort of what an object is and why we're doing what we're doing? Okay. So class of bear. So this is a new thing you haven't seen before. We're not defining a function, we're defining a class. And the most simple thing you can say is that the bear class is now defined. And you notice this gets executed as we're creating this class. A equals bear. It's just saying A is pointing to this thing called class, which lives in memory right now. That's not very useful. But A, open parentheses, close parentheses, creates an instance of a bear, and it puts it at a very specific location in memory. So now this is its own example, its own instance of that class. So is A an instance of a bear? Yes. Just like is instance 1.3 of float. Yes. So floats and bears are now just objects or classes. Okay. All right. So now we're going to associate some attributes with this instance of a bear that I just created. We'll call this bear Oski, and we'll set the fur color to be brown, and then we're going to print out the name. Okay. So we just created an instance of a class. And then we're going to, for that specific instance, overload some attributes associated with that.
Did you just create those attributes?
I just on the fly created those attributes. Those didn't exist in my definition of what a bear is. Later on, we'll see how we can actually do that. Okay, so now let's actually create a bear class that does what it did before, but we're also going to have a method associated with that. There's a special thing that needs to happen in all methods that are associated with classes, and you add this word self. It actually doesn't matter what word it is there, but self refers to the instance itself. And for now, just think about every time you make a function inside of a class, you're going to call that a method, and every one of those functions, even if it doesn't take any arguments, will actually take this one argument as self. Okay, so we're going to have a method now attached to this object or class called bear. So I just said a bear class is now defined. I'm going to create a new bear whose variable name is f, and then f is going to have a method associated with it now, which will be say hello. Okay, so this is a function that basically operates on that bear class. That's not all that interesting, right? Because we don't really know much about, and we haven't really used the fact that each one of these instances could be potentially different from each other, yet still share the same types of functions, which we call methods. All right, so let's take a look at this again. We've created this bear class. B is now a bear. We'll print what B is. We'll say hello. That's a function that's attached inside of bear. We'll actually call that. Ooh, that didn't work. That didn't work because I didn't call the method on an instance. I called the method on the class itself. And in this case, I would have need to pass along an actual example or an instance of a bear that knows how to say hello.
Before you created the method was defined there. When you try to run the method now, will it be available to A?
No, because A was created with a when I created that bear A at the very beginning, it was created when bear didn't know, when that class bear didn't know about it. So A dot say hello is what you're asking? It didn't know about it because I created the bear back then. So even though I have two bear classes that I created, and I think I just overwrote one, A is still a variable of that's an instance that's pointing to the old version of what the bear class was. All right, so that's kind of very basic. In fact, you don't typically use classes this way. You typically use classes, as I'll show you here. And almost all of the classes that you'll wind up seeing that have utility have an underscore underscore init method. The underscore underscore init method, like other of these special underscore underscore methods, gets called whenever you create an instance of a class. Let's see what that means here. So now we're going to do some more interesting things. So we're going to create a bear class again. So this is going to wipe out the other versions that we had before. When we create it, we're going to say we're creating a bear class. So this gets called whenever you wind up creating the bear class. And now we're going to have what we had before with say hello, which is a method. And this method is going to actually know the name of itself when we have an instance. And how does it know? It's because when we create an instance of a bear class, we're going to wind up calling implicitly this underscore underscore init. And the name of this method has to be underscore underscore init underscore underscore. And now we're going to have one argument, which is going to be name. We're going to essentially store for this instance the variable name, and we're going to give it the name of what was called with the argument. This can be called anything else. This would be called my name if we wanted to. So let's give this a try and just see what happens. So I created the bear class. Now A equals bear, open bracket, bracket, close bracket. What am I doing here? This is what is called instantiation of the bear class. Huh, that's weird. I try to call this init thing, which happened implicitly, but I forgot to give it a name. So let's give it a name. And a bear is born. And now A knows that its name is Judge.
So before we didn't need the judge part because we didn't have the init.
Exactly. We didn't have the init, and init required us to have that. So I could have now another type of bear, A. I should have called it B. Okay?
So init required a bunch of different attributes like weight, blah, blah, blah. You need to have all of them every time you create it.
Yep. So if I wanted to have keywords and arguments and all that other stuff to require that a bear is created with not just a name but a weight and other stuff, then here's where you would wind up putting it. You can always, once you create an instance of a bear class, you can always, for that specific bear, say .favorite food equals spam, and that specific instance of that bear now has an attribute that none of the other bears have, which is favorite food. So the nice thing is, even though I told you using global variables is not really a good idea throughout Python, there is kind of a notion of a global variable which is just contained to a specific class, and that's actually quite useful in many cases. So let's see what's going to happen now when I create the bear class again. So I'm going to set the population when I create the bear class at 0. So that means there's no bears in my universe. I'm going to, when I instantiate, that is with this init, I'm going to set the name of the specific bear to be name, which is the argument. And I'm going to bump up this global variable of the bear class called population by 1. And I'm going to set the number of the bear that I just created to be the current population. So the first time I create a bear, I'm going to bump up the population by 1, so the total population will be 1. And then I'm going to set the value of this number for that bear to be number 1. And now I'm going to know, as I create these various bears, where you were in the population creation. Okay? So we're going to run this thing. I'm going to create a new bear called Yogi. Hello, I'm bear number 1 of 1. My name is Yogi, prepare to whatever. Now we're going to create another bear called Winnie. And Winnie is going to say hello, and then bear Yogi is going to say hello. So A dot say hello. Hello, I'm bear 2 of 2. My name is Winnie. Hello, I'm bear 1 of 2. So now Yogi is aware that the bear population got created. So these are two separate objects, both instances of the same class, and they share some global properties that are associated with that class.
How did the population know it was global?
What's that? How did the population know it was global? Well, it was basically set inside here, and anything you set that's not part of a method is going to wind up being associated with that entire class. And these things are part of as part of the class as well, because these are functions that are part of that class, which we'll call methods. Yeah. Sure. So the question is, can we reset the population? So we could say a population is equal to -1. And let's see what a population is again. Let's see what B says the population is. It says it's 2. Let's see what bear says the population is. That also says 2. So A wound up getting its own notion of what it believes its local value is of the population. And that's actually, if I was going to create this inside, that would be self.population equals. But if instead I said bear population equals -100, and I said b.population, it's -100. What do you think A is? -1. So the local scope in this case, because I had a name conflict, wound up saying, I don't know if you mean global or local. I'm going to assume that you meant just this instance. Yeah. I'm sorry, I didn't hear you.
Can you specify the access monitors to these variables? Like, can you do something to prevent people from changing fast global variables?
No, there's no real way. Python makes everything public. So if you're thinking of it sort of with a Java paradigm, you can't have purely private stuff. Everything is effectively public, and that's just how the decisions that Python made. So right, so we know basically about these other. Let's set the bear population as it was to 2, and so we know that we can basically keep track of these things at effectively the global level. All right, so we're going to do create again a bear class, and we'll create 3 bears, ASCII, and now instead of having just 1 argument, we'll have 2 with a weight, and we're going to save 2 local variables for each of these instances. We'll take a look at my bears. That's just a list of all the bears. And now I can loop over the list of the instances of those bears, and I can look at the weight. And the total weight on all 3 of those things is less than 300. Total weight is 295. We could, if we wanted to, keep track of whatever the total weight is of all the bears. And every time we instantiate a new bear, we could say bear.tote plus equals weight. Okay? Let's try it again. And now, if this works, we should be able to say bear.tote, and we get 295. Yep. Of when they were instantiated, exactly. And so what you'd want to do potentially is, if you wind up creating a new method called gain weight, and you have to have this self, you'd say self dot weight plus equals 10. Actually, let's do this right. How much? Make that keyword. Now this would start not doing what you expect, because now the whole bear class isn't keeping track of that. What you'd want to say now is bear.tote plus equals how much. So you'd want to increment and decrement.
Does that mean every time you initiate a bear, all of the bears go up by 10?
No. So let's see what happens. So bear.tote is 295. Now let's say Winnie or Yogi gained some weight. And you see it didn't return anything. Now what's bear.tote? Okay, and c.weight has gone up. Okay? So the nice thing is you can contain, and oftentimes it's useful to think about the potential for these global variables, but the way to think about it is if you've got an instantiation of hundreds or thousands of objects all derived from the same class, each one of those can go off and do their own things independently of each other and keep track of these internal attributes as they need to. So we can have a class of a bear, we can have a class of a cat, class of a duck, and each of them know how to do the same method. So they've got the same name. So we create Oski, Bill, and Daffy. And now we can harmonize, create a new function called harmonize, where now we can call the vocalization method for each one of these, and they can do different things. So I can harmonize growl, meow, quack. Okay?
Is there a built-in function to list all the instances of a given class?
Is there what?
A built-in function to list all the instances of a given class?
Yeah, so is there a built-in function to list all the instances of a given class? So first of all, you could say bear dot, and you notice that I've got the tab completion. I could also do this, and I can see all the other things here. I believe bear.dir is what you need. Sorry, that's what? Needs to have an argument. Oh, because it needs an instance. So here are all the things that are available.
But that's not the instances of the class.
That's an instance of that class.
He's asking for all of the bears.
All of the bears. Can you list them? A, B, C.
Can I list what?
The list of the A, B, and C, Oski, and all the other names.
Oh, you want to know what the names are by looping over all the existing bears? I think you have to keep reference to all of those. So when you create those, you're assigning those to variables, or you could do those inside of lists. So I don't believe the bear class knows of all the instances that exist out there. You could keep a list within the bear class of pointers to all the ones that got created. Yeah.
You also filter the namespace by the types, things that are an instance of that class. So you can list all the things that are in the namespace.
Okay, let's try that. So you would want to just do like locals.
Right.
And then you would say x for x in locals if is instance x of bear.
Yeah.
Huh. Oh, wait, hold on. I think locals is different than what we thought. So that we actually want the key, right? The value, excuse me. If x value 0. Oh, thank you. There we go. Good idea. Does everyone see what we just did? So we said, well, if we want to find all the bears that are in our namespace, because we've forgotten all their variables or we've forgotten the locations of where they are, how do I find those? We looped over all the locals, all the local variables in the namespace, and we figured out, is this thing an instance of type bear? I'm not going to do the breakout problem. Instead, I'm going to jump to the second half of object-oriented programming. But let me ask if there are any questions while I set that up. You all got it entirely? That's great. I forgot whether I've got version 2 or not. I may be pulling up the wrong notebook here. Nope, I haven't pulled up the wrong notebook. Okay, so we have the notion of an init, and you can imagine the opposite of that is when I actually wind up deleting something. So here I'll wind up creating a bear, and it'll get a name. And when I wind up deleting that instance, I actually will wind up calling implicitly the __ del. So let me create bear yogi and bear cow, and I'm going to delete them both. We'll kill them off the population. And you see, even though I didn't actually call the method __ del, I effectively call the method because Python says, oh, if I'm deleting this object, I'm just going to look at what's inside, and if it's got a method that's defined, which is __ del, I'm going to actually run that method. Just like when you create an instance, you actually run the __ init. So here, I'm gonna actually assign y is equal to bear yogi, and then I'm gonna then assign it to equal Cal. What happened, I made a bear called Yogi, I made a bear called Cal, and so that's what happened here. And then I just needed to assign that to y, but Python said, wait, y is already pointing to another one. I better delete that instance, and that's where we wind up getting the bang Yogi is no more. Okay, so does everyone understand how that happened? Python is keeping track basically with what's called a reference counter under the hood of every time you're pointing to something. And when nothing is pointing to a specific place on memory, Python says the reference count is 0, I can garbage collect it and throw it out. And
So before you did y equals bear cow, if you did x equals y, then that one wouldn't be needed?
x equals y. Is that what you want to try?
And then now do y equals bear and bear.
So now do what? Y is equal to that?
Yeah.
So what are we trying to test here?
Now does the yogi not get deleted because x is pointing at it?
I made Yogi, bang, Yogi is no more. Well, remember, let's go. Let's just del x, del y, just in case. Okay, so now our namespace is clear. We're going to create y for the first time. And then we're going to say x is equal to y. So that's going to be pointing to the same bear Yogi. And then y is equal to bear. It's going to kill off Yogi, I believe. Because x is still just pointing, x is just pointing to that. It's not its own instance of it.
Except for your comment is that Winnie is no longer, whereas it should be Yogi.
That's because y wasn't actually deleted
Wha-
before.
Oh, I didn't kill. Oh, because I did it up here. Thank you. Let's try this again. Okay, we've killed everything off. Let's try it again. There we go. So it didn't get killed off because it's still got a reference pointing to it. If we quit and we get out, then actually you wind up calling the del. So there's a destructor that happens when you gracefully try to get out of Python, where Python looks at all the open files, says I better close those. It looks at all the instances that exist, it tries to delete those, and it tries to shut everything down. So having a del is pretty nice when you wind up wanting to be graceful. Just to be clear, init and del aren't supposed to return anything. They're just that's just by convention. All right, what's that? They will. You can't have a return statement in them. They will return none, but they're not. You're not supposed to give it a return statement. Okay, so let's do this again with some more interesting stuff here. So we've got a bear class. We're going to keep a log file associated with that. We're going to keep track of all the bears that exist. Here are all the bear names. So every time we call the init, we're going to save that name. We're going to open up a log file, append to that log file. We're going to bump up the bear population number. We're going to set the number of what the current bear population is locally. We're going to write to the log file. We're going to flush that log file. And then when we close it and delete that, we're going to close that log file. So now we've got potentially lots of bears all pointing to the same log file that are all open. And when I delete a bear, it's going to wind up closing down its own connection to that log file. But all the bears are doing appending to that log file. So they're not rewriting it each time. Bears will do some growling. And also you'll notice for the first time I'm introducing __str. This will be the string representation of that bear. So if I actually did str on the bear, instead of it just saying bear _ main, in some location, we'll actually have something potentially meaningful. All right, so I'm going to remove the bear log. I'm going to run this. Let me just create this here. I'm going to run bear. So now bear is in my namespace. So I'm going to create Yogi. I'm going to create another bear called Yogi. I'm going to ask the question. I'm going to set b equals to a. So that means I killed off one of the Yogis. Now I'll create fuzzy bear, ask what the bear num is, the population. So I've got two bears, one is Yogi and one is fuzzy. I'm going to delete those both out of the population. I've got 0 left in the population. And now I can see the whole history of what I just did. I saved it into a log file.
Why do you need to flush the log file again?
You need to flush the log file because if you write to a standard out or you write to a file and then you close it, it's a potential that the buffer won't actually get written. So what you're doing is you're writing it, but you're telling the OS, my intention is to write it here. You put it in whenever you're ready to do that. By flushing it, you're forcing it to flush. All right, so str is a method that defines how class should represent itself. So let's take a look at that. I made a bear called fuzzy, and now I'm calling the print function on B. The print function knows to look at the __ str method, and I created some meaningful answer for what it should be returning as. And you notice I didn't print within the __ str. I just return back. So unlike init and del, str needs to have a return which is of type string. Any questions about that? So let's create Yogi, and the bear population has been increased, and Yogi is the second bear. If I print this again for fuzzy, I wind up having a population of 2. Everyone got it? All right, let's do something a little bit more interesting now. You notice that if I keep on now calling the print on fuzzy, I'm going to wind up continuing to get the same thing. So this looks like this is static. But now I'm going to introduce the datetime module again, and I'm going to keep track of how long the bear has been alive. So the bear was created when it's instantiated. And then I'm going to actually figure out what its age is. And age is just the time now when this print gets called, minus the time that it was created. So let's take a look at Yogi. So it's only been alive for 2.58 seconds. Now it's been alive a little longer, a little longer, a little longer. So hopefully you can see some of the power of what you can do by having objects sort of know stuff about their birth and do things when they wind up getting killed off. You can imagine that there are many other special methods, and here are some of them, which basically tells Python whenever you see a plus sign, if you're doing the add, here's what it means to do a plus sign. So what does it mean to add 2 bears together? That's something that we get to define. So let's create an adder method. So that's going to say, let's create a cub, which is of type bear, which is an instance of type bear, whose name is going to be the progeny of the name that I was given, and then the other one that I'm adding it to. And then I'm going to store a new attribute called parents, which is just going to be pointers to the 2 instances of self and other. In multiplication of 2 bears together, we're just going to have the same notion of addition. Okay? So I'm just going to return whatever I get out of the addition. Let's see what happens here. So I'm going to create 2 bears, Yogi and Fuzzy. And they're going to have a child together. Y plus C. So this is now a notion that didn't exist before of what it meant to add 2 bears together. And I just made a bear who's called progeny of Yogi and Fuzzy. And if I look at our kid, it's got now the notion of parents. So let's look at what parents are. This is a location to the 2 instances of the 2 parents. And what's the name of parent 1? What's the name of parent 2? Yeah. Let's try. This is getting very sad. So shall we? We want to delete. Let's delete del y. What do you notice that didn't happen when I did a del y? Well, first of all, I didn't have a delete in here, so it didn't say anything. But let's take a look at the parents again. They're still there. It's because when I deleted y, there was still a reference to y somewhere else, and so it didn't yet delete it out of the namespace. So it still actually winds up existing. It still existed, even though I killed the notion of what y is. The instance of what used to be y is still around and still pointed to. So I can say that, let's see, our kid has a broken limb. That's true. And you can see that C doesn't have broken limb, doesn't exist. Right? So each individual object can take on its own attributes if it wants. Notice that we can do rkid1 multiplication. Y won't exist, so I have to create it again. It's the same thing as the adding, because that's how I just created it. So some other useful specials here. The underscore doc, that's the doc string. Underscore name, that's the class name. Module, that's where the class was defined. In this case, it's going to be underscore main because we're in interactive mode. Where it subclasses from, etc. Okay? I'm going to skip over this thing about hiding because there is one way to create a protected variable, but it's not exactly protected. There's ways to get access to that. Not that important. Let's just do a little bit more on referencing because we've been dancing around a little bit as people have been asking questions of like what happens if you del this, does it still exist? So let's create an instance of bear, Yogi, and that's some location on disk, that instance, right? B is equal to A. So, well, forget that was killed off because it was the old version of B. So now B and A are pointing to the same instance. And look at B. You notice that those are actually the same thing as A, the same location. ID gives you the kind of pointer location of where this lives in memory. So now A.name is fuzzy. What is B.name? Yep. B.bearnum. Remember, we're incrementing the bear populations. 1. Who wants to tell me why, even though I've got 2 bears, one's... What's that? It's still one instance. I didn't call the underscore init when I said B equals A. I only called underscore init implicitly when I instantiated A. Yes?
So how do you make a copy if you wouldn't want it to be a copy of them?
We're getting to that on the next line. So we'll import this thing called copy, and we'll say C is equal to copy.copy of A. So we're going to now create a copy of A. So this should be a new memory location. So we just created a copy of the instance somewhere. What do you think bearnum is? When you create a copy, you're not actually instantiating a new class. You're just saying whatever is in the memory associated with this instance, just map that to another place in memory somewhere. Okay, I didn't call the creation underscore init when I called copy. What's C's name? What's that?
You change the attribute of the copy.
That's what we're doing on the next line. You guys are good. So C.name, I'm leading horse to water here. C.name, fuzzy, because that's what A's name was before. Now if I say C equals smelly, what's A's name? Still fuzzy, because I just changed an attribute of an instance of type bear over here, but the original one is untouched. Now I'm going to create a list inside of A, which I can do, What's b.mylist? It's the same. What's c.mylist? Doesn't exist. It doesn't exist because A and B were pointing to the same place. I created a new attribute inside of A, and so B knew about it, but C is over here, and though it was a carbon copy of A at some point, now the two have diverged, and now C doesn't have that instance of my list. Now, what do you think the bare number is? Yeah. Still 1. Okay, so now I'm going to create another copy of A. Okay, so what is my list? Of course, it's now just a completely separate copy, right? And it also copied over what the list is. What's D's name, if you're keeping track? Fuzzy, good. Now I'm going to set D's name to Yogi. And A's name should be unchanged from before, right? Because that was just a copy. Now let me go back into A. And let me change my list. And now what's D my list? What? Ah! What happened? Anyone want to come up with a argument for why that just happened? Because the list has the same reference. So even though I created an attribute which was part of A and B knew about all the attributes that were there, I also created a list. And the list is a mutable object. And when you have a mutable object, what you're really doing is just creating a pointer to that mutable object. Okay? And so both A and D wound up pointing to another place on memory, which was the same place on memory. So D, my list, the idea of that is the same as A's location. Yeah?
So the attributes are stored as the values, the lists are stored as pointers.
Yes.
The values, strings?
Strings, well, we tried with the strings because we did that with the names, right?
Those are values.
Yes, because those are immutable objects. And so those wind up, every time you make a copy, wind up getting actually copied. Whereas when you make copies of mutable objects, you're actually just copying the location of the pointer.
So for weight, if we were to copy it?
A weight is a number which is also an object, and that's immutable. So that will also wind up. We can take a look at that if you want. Doesn't know what that is because I didn't overload it. Is this a bad thing? It's not a bad thing. You really need to understand this because oftentimes you'll want to make copies of instances of things, and I wanted you to at least see one time that this is not like, you have to understand what's happening internally to really get it. So if you're confused, that's okay, but at least you can go back to your notes and see that you've seen this before. There is the notion of a deep copy, which will recursively go through all, not just attributes that are mutable objects, but actual things that are pointed to, and then things that are pointed to inside of that. It'll make a full copy of that. So that should work here, except there's something weird where it's the notion of serialization. You can't wind up serializing or making copies of certain things. And in this case, we have a pointer to an open file handle. So if we get rid of that pointer, we should be able to make a deep copy and see that my list of that, and we wind up not changing it on another copy. Okay? What's the bare num? Still 1. All right, so I think I'm going to end with that, and I think we're fairly good on time with respect to lunch. We don't have any breakout sessions for lunch, so we'll wind up coming back at 12:55. Start with test-driven development. Any questions before we break? We did a lot this morning, so get some fuel for the afternoon. It's going to be fun.